Right, so question 9. A bag contains 9 discs, numbered 1, 2, 3, 4, 5, 6, 7, 8 and 9. Andrea chooses 4 discs at random, without replacement, and places them in a row. How many different 4-digit numbers can be made? Well, actually, we can attack this in a number of different ways, can't we? It's a classic permutations question. It's saying we've got 9 distinct items. We want to select 4 of them, or we want to see how many arrangements there are. So if you've got a kind of permutations and combinations head on at that point, you can just think, right, well, this is 9 items. We want to see about the arrangements of 4 of them, and so we can do that calculation. And if you do that, that is 9 factorial divided by 9 minus 4, so 5 factorial. You could do it straight away onto your calculator. My Aurora AX595TV has it above the times button. 9, shift, so P and 4, and we get 3024. Okay. But my instinct isn't automatically to think in terms of permutations and combinations, so I didn't do the question that way when I first saw it. The way that I did the question was I thought, well, 4-digit numbers, so when we choose the first digit, we have 9 choices of what the first digit can be. Once we've chosen the first digit, we've got 8 digits left, so we've got 8 choices of the second digit, 7 choices of the third digit, and 6 choices for what the 4th digit can be. And if you do 9 times 8 times 7 times 6, of course you get 3024. So however you think about these things, either way is just as good at arriving at your answer. Okay? That's kind of the way that my head approached that straight away. How many different odd 4-digit numbers can be made? Well, actually bear in mind that I was thinking along these lines, and so the way I thought about this is that, well, actually, as we choose our numbers now, it doesn't matter which kind of order I think about these numbers. This means that the last digit has to be an odd number. Well, the odd numbers are, oh, missed. There are 5 odd numbers. So my last digit, I can only choose in 5 ways. The other digits, I don't have that restriction on. So once the last digit is chosen, it's one of those 5, I've got 8 numbers left to choose the first digit, 7 left for the second, and 6 for the third. And so that must be the number of different ways. The last digit must be one of the 5 odd numbers that we're dealing with. If we work that out, that is 1680, I think. 5 times 8 times 7 times 6. Yeah. Okay. Actually, let's think. There are lots of ways that we can think about this. Let's be really logical about this. Out of these 3024, what proportion of those are going to be odd? Well, the chance of it being an even number, that's 4 out of the 9 final digits. The odd numbers is 5 out of the final 9. So we could just think it's 5/9 of 3024. We could do it that way. And if you do 5/9 of 3024, surprise, surprise, you get 1680. So there's often lots of different ways that you can think about these to get to the right answer. Okay, part 2. Andrea's 4 discs are put back in the bag. Martin then chooses 4 discs at random, without replacement. Find the probability that the 4 digits include at least 3 odd numbers. Okay. What we're saying now, actually, we're not doing a 4-digit number anymore, are we? We're just selecting 4 digits. So something essentially has changed about the question. We were talking in the first part about 4-digit numbers, so the order mattered. Now we're just talking about choosing 4 discs. So the order no longer matters. So let's start up with, we're doing probabilities here, so let's think how many different combinations of 4 cards, 4 discs, can I choose out of the 9? So the first thing to do is to work out our total. You see the order now doesn't matter. So my total is 9C4. Which, again, if you do that on your calculator, 9C4 is 126. You know, we could just say, up here, we worked out this number, there were 3,024 arrangements. But those 3,024, any kind of, all the different arrangements of every 4 digits that we get now look the same in this one, like 1, 2, 3, 4, 4, 3, 2, 1, 2, 3, 4, 1. We're not telling any difference between them. So what we could have done is done 3,024 divided by the number of arrangements divided by our 4 factorial. And of course you'd end up with the same answer there, don't you? 3024 divided by 4 factorial gives us, I can't work this calculator. That took a long time. 126. Okay, so you can see there's lots of different ways of arriving at the same answer. Right, that's the total number of possible selections that we've got. What are we after now? The 4 digits include at least 3 odd digits. Well, that could happen in 2 ways. They could be all 4 odd digits. So how many of these are all 4 odd digits? Well, that means out of the 5 odd digits, I'm choosing 4 of them. Which you could do on your calculator, but that must be 5, mustn't it? Because that means how many ways can we not select an odd digit? And there's only 5 ways, there's only 5 odd digits for us not to select one each time. The other thing that could happen is that we could have 3 odd digits. And that means out of the 5 odd digits, I'm going to choose 3 of them. And out of the 4 even digits, I'm going to choose 1 of them. So that's 5C3 times by 4C1. And we'll go to the calculator to do that. 5C3 times 4C1 gives me 40. Okay, so the number of ways that I could have done this to have at least 3 odd digits is 45. But we wanted a probability, so it's 45 out of the 126. And I don't think that cancels down, does it? Oh, it does. 5/14. That's my probability. Right. And the final part of the question said, find the probability that the 4 digits add up to 28. So we're choosing 4 numbers, they need to add up to 28. That's quite a big number for 4 numbers to be adding up to, because 28 is 4 sevens, isn't it? So they must all be fairly large numbers. So how could we do that? We need to actually, there was a similar question, remember in your trial exam in last summer's paper, where you had to think about actually quite a restrictive thing of writing down the possible ways that something could happen. Well, if we're going to get 28, well, let's try 9 and 8 and 7. would take us to 24. So we need to have 4. So 9, 8, 7 and 4. Now if we don't have the 9, we're not going to make it. Let's try not having the 7. Let's do 9. We do 9 and 8, that's 17, and 6, that's 23. And so we need the 5 as well. And there can't be any other ways that we could do this, can there? Because we wouldn't have enough numbers to get up there. So there's only 2 ways that the sum of the digits can be 28. And you can try a few more, try a few different combinations and see that they don't work. If we did 8, 7, 6 and 5, then that's not going to be enough, is it? Because the average of 8, 7, 6 and 5 is below 7, and 4 7s are 28, so that can't work. So they're the only 2 ways we could possibly do it. And so that's, well, probability 2 out of the 126. So 1 out of 63. And we don't need to go into any other kind of awkward probability theory things. We just work out the possible ways of doing it divided by the total number of options. That was it. That was the last question on that paper. And that's maths.